Okay, so good day everyone. We're going to have an additional example on flexural stress under beam stresses. So let us consider this example. So we have here a flat steel bar 1 inch wide by 1/4 thick and 40 feet long is bent by couples applied at the ends. So this is a far end. So the couple are applied at the far end so that the midpoint deflection is 1 inch. So compute the stress in the bar and the magnitude of the couples using the modulus of elasticity equivalent to 29 times 10 raised to 6 psi. So let us illustrate first the figure. So this flat bar has a length of 40 inches. So this will be our cross section, 1/4 inch thick with a width of 1 inch. So the force couple is applied. Say we denote that by M. It is applied at both far end of this flat steel bar, and it will have a symmetric elastic behavior wherein the maximum deformation is at the center or at the centroid equivalent to 1 inch. So that is the condition in the problem. So we should note that when we have a bending stress, of course there will be a radius of curvature, and that radius of curvature is referred to a point of origin in here. So if we consider this elastic geometry, therefore this will be the radius, and of course the centroid here is the radius of curvature from the elastic curve up to the point of origin. So of course rho here is composed of this dimension plus 1 inch. Okay, so recalling the general formula for flexural stress, we will be needing here this one, E over rho, because on the figure I think by geometry we can derive right away the value of this radius of curvature. So we're going to pair that into the side composing of moment divided by the moment of inertia, because here unknown is the moment, and I could be easily derived because we have the cross section. So by cross multiplication we will have an equation equivalent to M is equal to EI all over rho, wherein I, this is a rectangular section, this is equal to BH cubed all over 12. So we compute the width here is 1, and then the thickness is 0.25, that is cube all over 12. So we come up with an I equivalent to 1.3 times 10 raised to negative 3 inches raised to 4. So we are done with the I. For the rho, we will just have to use the Pythagorean theorem, because in here we have a right triangle. So considering the right triangle, of course rho here will be the hypotenuse, and the leg is the half of 40, so this dimension. So that will be squared plus the other leg, the vertical leg is rho minus 1. So this yellow dimension, vertical. So that is also squared by manipulation. So this 20 will become 400. We can cancel out rho squared. So this one is expanded to rho squared minus 2 rho plus 1. So that yung isang rho squared is cancelled. So we will come up with a value of 200.5 inches. So this is the radius of curvature. So little by little we have completed the variables that we need in order to come up with the magnitude of the couple, and that is m. So we simply directly substitute all of those values. So we have E, 29 times 10 raised to 6. This is PSI, pounds per square inch. And then I is inches raised to 4. So consistent tayo with the PSI. And then rho here is 200.5 inches. So what is important here is all of the terms will be in terms of inches. And then by calculation, we come up with the value of the moment, that is 188.03 pound inch. So that is one of the unknown. We proceed to the corresponding bending moment. So this time, we're going to utilize the central equation to pair it with mi, wherein we need the value of y. Remember that y is the farthest distance of from the neutral axis. So it is understood here that this is rectangular, so that the centroid will just be half of the thickness. So the thickness here is 0.25. So we divide it by 2, that is 0.125 inches. So by cross multiplication, so this is the bending moment, bending stress equation. We have my all over I. So we simply substitute the values, 188.03 times 0.125 divided by the derived moment of inertia. Okay, so again, by manipulation, we have bending stress is equal to 18,079.81 pounds per square inch. So that's it for this first problem. So it is simply utilizing this formula, this general formula. So we just have considered what are the given, and then select the side of this general formula. So moving on to another problem. Again, this is an example of bending stress. In a laboratory test of a beam loaded by end couples, the fibers at layer AB in the figure are found to increase at 60 times 10 raised to negative 3 millimeter, whereas those at CD decrease 100 times 10 raised to negative 3 millimeter in the 200 millimeter gauge length, using modulus of elasticity equivalent to 70,000 megapascal, or that is equivalent to 70 gigapascal. Determine the flexural stress in the top and bottom fibers. So the layers here in the figure are already specified, and is observed that this is a symmetrical location when we consider the neutral axis. Of course, the involved formula here is this one. Y is the farthest distance. Y is the distance of the point of consideration up to the extreme fiber. So when we say extreme fiber, it could be either the top fiber or the bottom fiber. So meaning it is just the outer fiber. Okay. So illustrating the deformation, it says in the problem that the top portion will have an increase, while for the bottom we have a decrease. So the values are specified. So 60 times 10 raised to negative 3 for the layer AB on top portion. For CD, that's 100 times 10 raised to negative 3 millimeters. So by the sign alone, we can see the behavior of this particular fiber or member. Okay. So, dalawa lang naman ang pwedeng maging behavior nito. It could be either concave downwards or concave upwards. So, why is it that we have concluded that this is concave downwards? Because, yun nga, increasing yung deformation, meaning lengthening. So, when it is lengthening, of course, that is a tensile. And if it is decreasing or decreased deformation or decreased length, meaning it has shortened. So the orientation is compression. So with this condition, of course, we can say that the fiber is concaving downwards because the upper portion will be stretched and the lower portion will be compressed, and that is what is given here. Now compress yan because again this is a decrease, and this one has lengthened because this is a positive value. Now this is the zero deformation. This is positive and that is negative. So in here, we have actually labeled the unknown dimension considering the triangles formed out of this diagram. So why do we need to do that? Because by and by, we are going to utilize the triangle. Of course, gustong-gusto natin na may triangle because we can utilize bisimilar triangle principle or by ratio and proportion. So we still do not know the value of x at the top. X here is referred from the neutral axis or the vertex of the upper or the common vertices of this upper and lower triangle. No? So we denote that by x. Okay? So that yung nasa baba is 120 minus x. Okay? So single variable lang ang expression ng upper at lower. Okay? Otherwise, we cannot simplify our equation. Okay, so x is the upper dimension of this shaded portion, and then 120 minus x is the lower dimension of this lower triangle. So that we can now employ ratio and proportion. So we can say that x is to 60 times 10 raised to negative 3. So vertical muna versus horizontal. So for the other triangle, vertical muna, what is the vertical? 120 minus x versus horizontal, 100 times 10 raised to negative 3. So by cross multiplication and manipulation, we can have x is equal to 45 millimeters. Actually, ito pwede nyo gamitin yung you may take advantage of your calculator by shift solve method. Okay. So next, we're going to label the dimension of the overall height of the top triangle and the bottom triangle. Why again? Mamaya, we're going to utilize ratio and proportion. Okay? So for the upper triangle here, the dimension is x plus 30. So paano nakuha yung x plus 30? So we have denoted that this is x. So the overall height of that one, we'll just have to add 30 here. So that is x plus 30. While in the bottom overall length, that is 150, ito 150 hanggang A. So if we are concerned with the neutral axis, we'll just deduct here x. So that is 150 minus x. So by this, we can now determine the delta top by ratio and proportion. So delta top is to x plus 30. Okay, so the overall width and the overall height of the upper triangle. So we proportion it to the smaller triangle as a portion of this upper triangle. So we have 60 times 10 raised to negative 3 is to x, wherein x was derived to be equal to 45. Okay, so notice here, ang unang tina-target natin is delta. Okay, so delta top and bottom. Why? If we know the corresponding deformation at each of the portions, say top and bottom, by and by, or in a while, we are going to determine the flexural stress out of that. Likewise, we can use the ratio and proportion for bottom. Okay, so delta bottom is to the overall height, that is 150 minus x, is equal to the horizontal 100 times 10 raised to negative 3 of this portion is to 120 minus x. So ito yung 120 minus x. So we substitute 45, and by manipulation we can derive delta bottom. So we have now the two top and bottom deformation. So let us note here that the top deformation is lengthening and the bottom deformation is shortening. So as you can see here in the diagram, ito na-compress, yung upper portion is humaba. By the way, this red line here is actually the neutral axis, meaning neutral. The stress is 0. So when the stress is 0, hindi siya humaba, hindi siya umikli. So neutral. Okay? And then by Hooke's law, we can now derive sigma. So ito, galing yan sa general formula. Okay? So by Hooke's law, remember Hooke's law is the condition where the stress is proportional to the strain. Okay? That is why E is equal to stress all over strain. Hence, strain is equal to deformation all over the length. Okay? So ito, sinubstitute ko lang na yung length niya or the gauge length in the problem is actually 200 millimeters. Okay? So, by manipulation, ang concern natin dito is bending stress. So, by cross multiplication, we have bending stress is equal to E times strain, or the modulus of elasticity times strain, and then strain would be expanded to delta all over L. So, therefore, bending stress is equal to E times delta all over L. So this will now be the key formula for us to derive the flexural stress in top and bottom fibers. Okay, so in the top and bottom fibers. For top, we'll just have to substitute. E here is 70,000 times 0.1. 0.1 is here is the delta on top, okay, this one, divided by the gauge length, that is 200, okay. So by manipulation, bending stress is 35 megapascal. So this is actually in tension. So likewise, for compression or for bottom fiber, we have bending stress is equal to 70,000 times the delta 0.14 divided by the gauge length 200. So therefore, bending stress at the bottom portion is 49 megapascal. That will be compressive in orientation. So I think this ends this problem. So thank you for listening and have a good day.